Howdy folks, Zach here. This past week we were introduced to part 1 of the fundamental theorem of calculus. Remember, when we started talking about integrals, we were motivated by this problem of finding the area under a curve between two values, let's say x equals a and x equals b. This is a tricky problem because the region itself may not be a nice shape at all, right? It might be all curvy and irregular. However, we had this sneaky idea of splitting the region into rectangles. By slicing it into rectangles and adding up their areas, we could approximate this area under the curve decently well. The more rectangles we use, the better the approximation. And with infinitely many rectangles, the answer becomes exact. This led us to the following definition, which we're referring to as the definite integral of our function. It represents the area under the curve. Now, this was all well and good, but we quickly learned that our definition was a bit of a nightmare to work with computationally. Fortunately, we were saved by the following incredible theorem, part 1 of the FTC. It states that evaluating an integral is actually as simple as finding a function whose derivative is this little f. Then you plug in the bounds, b and a, and take the difference. We call this new function an antiderivative of little f. Now, while this theorem is incredibly useful, it might also feel a little bit mysterious. After all, why should the problem of calculating an area have anything to do with derivatives, which were about slopes and rates of change? It's true that the connection is surprising, and this is actually one of the reasons why the FTC is so amazing. It establishes a connection between two ideas that on the surface seem unrelated. While I'm not going to prove FTC in this video, I will attempt to convince you that it's true by looking at an applied example, the distance traveled by a car. By looking at something concrete and then returning to this theorem in the abstract, as it's written here, I think you'll come to find that this result isn't quite as mysterious as you once thought. Okay, folks, consider the following warm-up example where we're given a car's velocity time graph and we're being asked to find the car's change in distance, its displacement, from t equals 0 seconds to t equals 5 seconds. Velocity here is in meters per second, it's on the vertical axis, while time is in seconds on the horizontal axis. Now, this is really just meant to be a stepping stone for something a bit more complicated to follow. It's not a terribly hard example, it doesn't require any calculus. Take a second to pause and see if you can answer this one yourself, then we'll take it up together. Okay, the key here is to observe that this car is traveling at a constant velocity. Hence, its displacement is given by its velocity times the change in time, a formula that you may know from physics. The velocity is 50 meters per second. We multiply that by the change in time, which is 5 seconds, and we get a total displacement of 250 meters. Cool. Now, something to note here is that we can actually see the car's displacement in this velocity time graph itself. Indeed, we calculated the displacement by multiplying this height by this width, meaning the displacement can be seen as the area under this curve. If you're feeling good with this, folks, let's introduce some calculus in a slightly spicier example. Okay, we now have a very similar type of problem, but this one has a twist. This car is now no longer moving at a constant velocity. Its velocity is increasing as a function of t. Finding the total displacement of this car is actually quite a bit more complicated, since velocity times time, that formula that we know for distance, really only works when the velocity is constant. It's therefore a bit tricky to study this car's journey all at once. Its velocity is simply changing by too much over the entire interval of time. But herein lies the trick. We can instead study the car's movement over a bunch of tiny little intervals of time, not over the whole thing all at once, but over tiny little segments. For instance, maybe we first analyze the car's movement just in the first 1 second of time, then in the second second of time, then in the third second of time, and so on all the way between 0 and 5 seconds. Over each of these tiny little chunks of time, the car's velocity probably isn't changing by too much, so I think we could reasonably pretend that this velocity is essentially constant on each one of these tiny little intervals. We could use, say, the car's velocity at t equals 1 as the approximate velocity over this first interval, the velocity at t equals 2 as the approximate velocity over this second interval, and so on. The upshot of this is that since we're pretending that the car's velocity is constant on each of these chunks, we can use our distance equals velocity times time formula to figure out how far the car is moving in each little chunk of time. In the first interval of time, the car's displacement is this velocity here times this change in time, delta t, which we visualize as this little area, the area of this rectangle. On the second interval of time, the car's displacement is this velocity times delta t, which is the area of this rectangle, and you rinse and repeat. You can then add up all of these little displacements, all of these little areas, to estimate how far the car has traveled over the full 5 seconds. This approximation, of course, isn't perfect. It looks like we're overestimating the distance by a little bit, but you can improve the approximation by considering shorter and shorter intervals of time. In other words, more and more rectangles. If you take a limit of these approximations as you use more and more rectangles, you'll find that the car travels exactly 175 meters during its journey. Folks, this should feel very familiar. It's exactly the process we went through when figuring out the area under a curve y equals f of x. And indeed, you can see that's what we're doing. Just like in the last example with the simpler car, the displacement here can be visualized as the area under the curve. The displacement is the integral of the velocity function. And, as this notation reminds us, we're calculating that displacement as a limit of a sum, that's what the integral sign should remind you of, a sum from x equals a to x equals b of, well, we're adding up velocity times a little change in time, a sum of tiny little distances. I'll just briefly mention that this process works even for velocity curves that are negative for a period of time. A negative velocity just means that our car is moving in reverse, so we're actually losing a bit of our total displacement over this chunk. Still, you can calculate the total displacement in the same way as before, by summing up and taking a limit of those rectangular areas. Here, the rectangles will have a negative area since we're using a negative velocity to represent the rectangle's height. Thus, I suppose it would be a bit more correct to say that the displacement is not the area under the velocity curve, but rather the signed area under the velocity curve, with any area below the horizontal axis counting as negative area. Okay, folks, let's take a step back and think about what we've learned from our examples. If we want to know the displacement of a car over an interval of time, we're effectively finding the area under its velocity curve. We're calculating this integral. One way to do that is by adding up and taking a limit of tiny little distances, which appear in our graph as tiny little rectangle areas. Of course, there is another, much easier way that we could have done this calculation, at least in theory, if we happen to know the car's position function, which I'll call s of t. We could simply calculate the car's displacement as s of 5, the car's ending position, minus s of 0, the car's starting position. Do you agree? The change in position would also be equal to the displacement. Putting these observations together, the area under the velocity curve is the car's displacement, which can be calculated very easily as s of 5 minus s of 0 if we happen to know this position function. Notice, folks, that this magic position function that provides a quick answer to this calculation is exactly an antiderivative of v of t, since velocity is the rate of change, or the derivative, of position. Folks, we've just naturally uncovered a quicker way to do these displacement or area computations. Let's summarize our findings in a theorem. I'm going to call our new theorem the fundamental theorem of velocities, or the FTV. It states that if v of t is the velocity of a car at time t, then the area under that velocity curve from t equals a to t equals b, which is denoted by this integral, can be calculated simply as the difference in the car's position, s of b minus s of a, right? It's the net displacement of the car. Importantly, this works for any velocity function. Our car can have positive velocity, negative velocity, whatever. Velocities of cars do tend to change continuously, but I suppose that's the only real condition of this v of t function in order for our theorem to work. Now, imagine we share our brand new result with a mathematician. The mathematician doesn't care so much about cars or velocities. They want a theorem that says something about functions and areas more generally. What can they extract from our result? Well, the mathematician notices that since any continuous function can be viewed as the velocity of some car, they could phrase the theorem to be about any continuous function. They change the first part of the theorem to read, if f is continuous. They also take this opportunity to rename v to f, since they won't necessarily be thinking about velocity in their examples, and they change all the t's to x's, since they won't necessarily be thinking about time. Next, they remember that if this function f of x were the velocity of some car, the integral, or the area under that curve, could be evaluated by finding this position function, an antiderivative, and plugging in the bounds. Again, since the mathematician won't necessarily want to think about position in all of their applications, they choose a more general name for the antiderivative, capital F, but they keep the rest of the theorem the same. By imagining little f of x as the velocity of a car, they've come up with this more abstract result about areas. They've also come up with a new name for the theorem so we can't sue them. They call their result the fundamental theorem of calculus. Folks, this brings us to the end of our lesson. The fundamental theorem of velocities is, of course, just a name I made up, but I hope it goes to show that this idea of using antiderivatives to find areas isn't totally random. It can be derived very naturally by exploring something concrete. Cheers.